In a three-phase, four-wire electrical system, understanding the concept of neutral current cancellation is crucial. The article you reference discusses this phenomenon in the context of balanced three-phase systems. The key idea is that in a perfectly balanced system, the three-phase currents are 120 degrees out of phase with each other and ideally equal in magnitude. These phase currents flow in each of the three-phase conductors and return through the common neutral conductor. When these three currents are added together as phasors, which are rotating vectors that represent the magnitude and phase angle of the alternating current, they theoretically cancel each other out. The resulting net current in the neutral wire should then be close to zero. This does not mean that there is no current flowing in the phase conductors or that electrical devices will not operate. Each phase conductor still carries current to power the loads connected to that phase. The lights and other equipment connected to the phase conductors will operate normally. The statement that the measured resultant current is equal to zero refers specifically to the current in the neutral conductor under ideal balance conditions. The reason this cancellation occurs is due to the 120-degree phase difference between the three currents. Imagine three waves, each offset by 120 degrees. At any given instant, the sum of their magnitudes will ideally be zero if the system is balanced. However, it is very important to note that perfectly balanced conditions are rarely achieved in real-world electrical systems. Any imbalance in the loads connected to the three phases will result in current flowing in the neutral conductor. This is why electrical codes and best practices require the neutral conductor to be properly sized to handle potential neutral currents. The practice of sharing a neutral conductor among multiple 120 volts branch circuits is permitted under certain conditions by electrical codes such as the National Electrical Code, or NEC. This practice, sometimes called a multi-wire branch circuit, involves using a single neutral conductor to serve two or three 120 volts branch circuits that are each fed from a different phase of a three-phase system. The intent is to take advantage of the neutral current cancellation effect. If the loads in the three phases are perfectly balanced, the neutral current will be minimal. However, as mentioned earlier, perfect balance is rare. If the loads are not balanced, the neutral conductor will carry the unbalanced current. Therefore, there are limitations and requirements in the NEC to ensure safety. For example, the NEC requires that multi-wire branch circuits only supply line to neutral loads. Also, the circuit breaker protecting the multi-wire branch circuit must simultaneously disconnect all ungrounded conductors of the circuit. This is typically achieved by using a two-pole or three-pole circuit breaker. While sharing neutrals can save on wiring costs, it is generally considered a best practice to run a separate neutral conductor for each branch circuit. This avoids potential problems with neutral current and voltage drop, and it provides a more robust and reliable electrical system. Regarding the oversizing of the transformer neutral connection to 200% of the phase current rating, this recommendation is related to the presence of harmonic currents in the electrical system. Harmonic currents are currents with frequencies that are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. Nonlinear loads, such as electronic devices, computers, and variable frequency drives, generate harmonic currents. These harmonic currents can cause a variety of problems in electrical systems, including increased heating of conductors and equipment, voltage distortion, and interference with communication systems. One of the most significant effects of harmonic currents is that they can add arithmetically in the neutral conductor of a three-phase, four-wire system. Unlike fundamental frequency currents, which tend to cancel each other out in a balanced system, certain triplet harmonics, which are odd multiples of the third harmonic like third, ninth, 50th, etc., do not cancel out. Instead, they add together in the neutral conductor. This can result in a neutral current that is significantly higher than the phase currents. To account for this increased neutral current due to harmonics, it is common practice to oversize the neutral conductor in the transformer winding in the service entrance. The recommendation to rate the transformer neutral connection at 200% of the phase rating is a conservative approach to ensure that the neutral conductor can safely handle the expected harmonic currents. However, it is not typically necessary to oversize individual branch circuit neutrals to the same extent. The harmonic currents generated by individual loads will typically be attenuated by the time they reach the main panel board. However, it is still a good practice to use conductors that are rated for at least 125% of the maximum load current for branch circuit neutrals. This provides a margin of safety to account for any potential imbalances or future load increases. There are several factors to consider when determining the appropriate size of the neutral conductor in an electrical system. Firstly, the expected load current on each phase. Secondly, the potential for unbalanced loads. And thirdly, the presence and magnitude of harmonic currents should be taken into account. Additionally, electrical codes such as the NEC provide guidelines and requirements for neutral conductor sizing. NEC Section 220.61 provides requirements for calculating the neutral load. The NEC also contains tables, such as Table 310.16, that specify the allowable ampacities of conductors based on their size and insulation type. It is important to consult with a qualified electrical engineer or electrician to ensure that the neutral conductor is properly sized for the specific application. In summary, understanding neutral current cancellation, neutral sharing, and neutral sizing is essential for designing and maintaining safe and reliable three-phase electrical systems. While neutral current cancellation can occur under ideal balanced conditions, it is important to account for potential imbalances in harmonic currents. Sharing neutrals in branch circuits is permitted under certain conditions, but it is generally recommended to run a separate neutral conductor for each circuit. Finally, oversizing the transformer neutral connection is a common practice to mitigate the effects of harmonic currents. Always consult with qualified professionals and adhere to electrical codes to ensure the safety and reliability of your electrical system. When sizing branch circuit conductors, it's important to adhere to the National Electrical Code, or NEC, which provides guidelines for safe and effective wiring practices. The NEC outlines several factors to consider, including the ampacity of the conductors, the type of load being served, and the presence of any voltage drop. Firstly, the ampacity of the conductors must be sufficient to carry the non-continuous load plus 125% of the continuous load. A continuous load is defined as a load that operates for 3 hours or more at a time. This requirement ensures that the conductors do not overheat due to sustained high current flow. Secondly, the type of load being served will also affect the conductor sizing. For example, motor circuits have specific requirements for conductor sizing to account for the motor's inrush current during startup. The NEC provides tables and guidelines for sizing conductors for various types of loads. Thirdly, voltage drop should also be considered when sizing branch circuit conductors. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times the length of the conductor in feet times the current in amps times the resistance of the conductor per foot divided by 1000. The resistance of the conductor per foot can be found in NEC Chapter 9, Table 8. In addition to these factors, it's also important to consider the ambient temperature and the number of conductors in a raceway or cable. The ampacity of conductors must be derated if the ambient temperature is higher than 30 degrees Celsius or if there are more than 3 current-carrying conductors in a raceway or cable. Derating factors can be found in NEC Table 310.15b3. Remember, always consult the latest edition of the NEC and work with a qualified electrician to ensure that branch circuit conductors are properly sized for the specific application. Proper conductor sizing is essential for the safe and reliable operation of electrical systems. The term K-factor mentioned in the original question refers to a transformer derating factor that accounts for the presence of harmonic current. Transformers are designed to operate at a specific frequency, typically 60 Hz. When harmonic currents are present in the electrical system, they can cause additional heating in the transformer windings. This additional heating can reduce the transformer's lifespan and potentially cause it to fail. The K-factor is a numerical value that indicates the transformer's ability to withstand the effects of harmonic currents. A transformer with a higher K factor can handle more harmonic current than a transformer with a lower K factor. To determine the appropriate K factor for a transformer, you need to analyze the harmonic content of the load it will be serving. This can be done using a harmonic analyzer, which measures the magnitude and frequency of the harmonic currents. Once you know the harmonic content of the load, you can select a transformer with a K factor that is high enough to handle the harmonic currents without overheating. It's important to note that K factor is just one factor to consider when selecting a transformer. You also need to consider the transformer's voltage rating, kVA rating, and impedance. Always consult with a qualified electrical engineer or electrician to ensure that you select the appropriate transformer for your application. Regarding the use of a 200% rated neutral on the supply to a transformer, this is primarily to mitigate the effects of harmonic currents, particularly tripling harmonics. These harmonics, which are odd multiples of the third harmonic, like the third, ninth, 15th, and so on, have a unique property in a three-phase system. Unlike the fundamental frequency currents, which ideally cancel out in the neutral conductor of a balanced system, tripling harmonics do not cancel. Instead, they add arithmetically in the neutral. This additive effect can result in a neutral current that is significantly higher than the phase currents, potentially overloading the neutral conductor if it is not adequately sized. To address this, electrical codes and engineering practices often recommend or require oversizing the neutral conductor and, in some cases, using a neutral conductor that is rated for 200% of the phase current. This ensures that the neutral can safely carry the increased current caused by the tripling harmonics without overheating or causing other issues. The 200% rating is particularly relevant in systems with a high proportion of nonlinear loads, such as those found in modern office buildings with computers, electronic devices, and LED lighting. These devices tend to generate significant amounts of harmonic currents. In contrast, for individual branch circuits, the necessity of oversizing the neutral to 200% is less critical. While it's generally a good practice to ensure that branch circuit conductors, including the neutral, are adequately sized to handle the expected load, the harmonic content on individual branch circuits is typically lower than at the main transformer or service entrance. Therefore, a more moderate approach, such as using conductors rated for at least 125% of the maximum load current, is often sufficient for branch circuit neutrals. However, if a specific branch circuit is known to serve a high proportion of nonlinear loads, it may be prudent to consider oversizing the neutral to a greater extent. Ultimately, the appropriate sizing of neutral conductors should be determined based on a thorough analysis of the expected load and harmonic content, as well as compliance with the relevant electrical codes and standards. Consulting with a qualified electrical engineer is always recommended to ensure that the electrical system is designed and installed safely and effectively.